Welcome to Quantum Field Theory. My name is Cedric Simonel. I'm the convener of this course and I will co-teach it with Joe Hope. Let me first acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respect to the elders past, present and emerging. Some information about this course. So the lectures are online in the EDX platform. We will have a workshop per week and also a drop-in tutorial. And regarding assessments, few words about books. The first one I recommend is Quantum Field Theory for the Gifted Amateur by Lancaster and Blundell. It's very pedagogical. It's probably the one I will encourage you to read if you want to self-teach quantum field theory. It's relatively easy. And it has some examples, of course, in particle physics, but also in condensed matter. It has some very useful appendices, for instance, for complex analysis. It starts with a standard approach, which is based on canonical quantization before moving to many-path formulation of quantum field theory. In this course, however, we will start with many-path formulation of quantum field theory. That's what is done in this other book, Quantum Field Theory in a Nutshell by Anthony Z. It's more about concept. It will have interesting discussion about gravitation. It has a tendency to skip some details and hide the dirt under the rug, but it's quite pedagogical and has very insightful discussions about quantum field theory. It starts with Feynman path integrals like in this course. Finally, another book is Introduction to Quantum Field Theory by Peskin and Schroeder. This is a classic. It's very focused towards particle physics. It's very good to teach you how to calculate Feynman diagrams. It's quite rigorous and detailed, but a bit hard, in particular for a first reading. It goes fast, in particular at the beginning, but it's good for advanced stuff. It starts with canonical quantization. Historically, quantum field theory was introduced to merge quantum mechanics and relativity. So you can pause this video and ask yourself, what are your takeaway messages from special relativity and quantum mechanics? As for myself, the takeaway messages for special relativity are that speed of light is constant in all inertial frame, nothing can go faster than speed of light, space and time are symmetric or have to be treated in a similar way, and we have an equivalence between energy and mass. In quantum mechanics, probably the most striking point for me is that we can have an object at several places at once, and we have also this wave-particle duality. The first attempt to merge quantum mechanics with special relativity was simply to build a relativistic quantum mechanics. So if you remember, Schrödinger proposed a non-relativistic version of quantum mechanics. So its wave equation is non-relativistic. It is based on an expression for the kinetic energy, which is non-relativistic. It's p squared on 2m. And it describes the evolution of a wave function interpreted as an amplitude of probability for the particle to be found at some position of space. So if you generalize that to a relativistic framework, you start with an expression for the energy which is relativistic, and that leads to the Klein-Gordon equation, which was first proposed by Schrödinger, and also to the Dirac equation, which is linear in the derivatives of the wave function. But these frameworks are still based on wave functions, so the same interpretation as in non-relativistic quantum mechanics. The problem with wave function is that no matter how hard you shake, bake, steer the Schrödinger, Klein-Gordon or Dirac equation, you will never be able to create new particles or to make them disappear. And that's not matching what we see experimentally. So if you collide two particles with enough energy, you can create new particles. You can also have them decaying or even transformed into other particles. Another problem of quantum mechanics is that you have an asymmetric treatment of space and time. Space is unobservable, time is a parameter. If you think about it, in quantum mechanics, you never have a time operator. The third problem is the causality. We will come back to that a little bit later, but even in relativistic quantum mechanics, you can have a particle which goes faster than speed of light, and therefore that breaks the causality because the consequence can happen before the cause. Another problem is that the Klein-Gordon and Dirac equation admit negative energy solutions. So a free particle can have a negative kinetic energy, and it will have no ground state anymore, and therefore its kinetic energy will go to minus infinity. Finally, we usually treat atoms with particles and light with a field. And well, physicists just like it better when everything is in the same bag. So either everything has particles or everything has fields. So if you summarize these 5 problems, you have particle can live and die, asymmetric treatment of space and time, causality, negative energy solution, asymmetric treatment of particles and electromagnetic fields. If you look at the problem 1, 2, and 5, that gives us a hint that we should abandon the concept of a wave function for a particle. If you look at the problem 2 and 5, that gives us a hint that we should use fields instead. But the problem with fields is that we don't necessarily have particles anymore. Remember that in quantum mechanics, we know that we should have wave-particle duality, which was proposed by de Broglie, not de Broglie. And when we have a wave function, that's all good because we have an amplitude of probability for a particle to be found in some position, and that obeys a wave equation. So both aspects of wave and particles are treated in the case of quantum mechanics. When we have field theory, however, takes for instance an electromagnetic field, this is a function of space and time, which are both parameters. That's not like a wave function, because in a wave function, the space is unobservable. So a field could easily describe a wave because that can be plugged into a wave equation. However, how are we going to get particles from a field? That's going to be one of the main questions in this course. So quantum field theory was introduced essentially in the context of particle physics. And that's because most of the processes in particle physics are usually relativistic. However, this is not a course in particle physics. Nevertheless, we are going to introduce most of our concepts and tools in the framework, in the context of particle physics. So for instance, we are going to focus on one specific reaction, which is a collision of an electron with a positron, which disappears and are suddenly transformed into a muon and an antimuon. The corresponding Feynman diagram is given on the right of the figure. The reason we choose this specific reaction is that it's the simplest one we can calculate. So we could go there relatively quickly in a couple of hours, give all the concepts and tools necessary to calculate this specific reaction. However, we are going to take our time, and in doing so, we will discover what we interpret as particles in quantum field theory, what's the origin of the forces, we will solve the problem of causality, and we will also see the relationship between spin and statistics. And as I said, it's not a course on particle physics. In fact, nowadays, most of the quantum field theory is done in the framework, for instance, of condensed matter and atomic physics, cold atoms, nuclear physics, etc. So we will spend also some time talking about non-relativistic systems of many particles, again, atomic nuclei, cold atom, condensed matter, and exhibiting some interesting properties like superconductivity, superfluidity, phase transition, etc. These systems are essentially non-relativistic, but nevertheless, when you take the non-relativistic limit of quantum field theory, of relativistic quantum field theory, you don't necessarily recover quantum mechanics as usual. You will recover a different framework which involves non-relativistic quantum fields as operators. We will also spend some time talking about effective field theory, which is how to integrate out the high energy physics and in order to focus on the low energy physics. And we will also introduce methods like the mean field approximation, because if you want to solve the many-body problem, well, it's just too complicated. So there are a lot of basic questions which you may have had for a long time when you started doing some physics. And we will answer these questions thanks to quantum field theory. For instance, we will see why all the electrons of the universe are the same, are identical particles, or, if you prefer, are not distinguishable from each other. We will see why gravitation and Coulomb interaction are in 1/r. We will see why same charges repel. We will see why we fall due to gravitation. We will also solve the problem of causality, and we will see why bosons have integer spins and fermions have half integer spins. We will also be able to calculate actual lifetimes of particles and cross-sections for some processes. But is that all? The answer is clearly no, because we are only merging quantum mechanics with special relativity, not general relativity. And that we don't know how to do that. Perhaps the solution will be string theory or another theory, which is yet to be discovered. In this course, we will cover quite a lot of formalism, so we need to agree on the notation we are going to use. The first notation which comes into mind is natural unit. We are going to set h bar equals c equal 1. And I let you pause and have a look at these different quotes. We will usually work in 4 space-time dimensions, so 3 dimensions for space and 1 for time. We will write Lorentz 4 vectors with italic letters like space-time coordinates and energy momentum. We will use Euclidean vectors with an arrow or with a bold letter. And when there is no ambiguity, the 4-vector x will be called the position instead of the space-time coordinate, and the momentum vector k instead of the energy momentum. Greek letters are used for Lorentz indices, they start from 0. Roman letters are used for Euclidean vectors, they start from 1. We use Einstein summation convention, meaning that repeated indices are summed. That's true both for Lorentz indices and Euclidean indices. The Minkowski metric is defined with a plus minus 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 signature. That's the opposite of the convention you have usually in general relativity. And because we only have special relativity, we have a space-time which is flat. Therefore, the metric g mu nu is the same as the Minkowski metric eta mu nu. Lorentz 4 vectors are naturally erased, meaning that when the Lorentz index is up, you have a plus sign in front of the spatial component of the vector. When you lower the index using the metric, you then get a minus sign in front of the spatial component. The covariant derivative is defined as a derivative with respect to x mu, and it is naturally lower, meaning that in this case you have a minus sign when the Lorentz index is up and a plus sign when the Lorentz index is lowered in front of the spatial derivative. You define the inner product between two 4 vectors as usual using the metric.